Okay, so we just finished the chain rule, which told us that we have a composite of functions. We had to take the derivative of the outside times the derivative of the inside. But what happens when we don't have y equals a function of x? What happens if we have an equation that's actually an ellipse for this particular situation, centered at the origin, and the top part of the ellipse, when we solve, y squared equals 4 minus 2x squared, we get the top half is the positive square root of 4 minus 2x squared, and the bottom half of the ellipse is the negative square root of 4 minus 2x squared. We technically have two different functions. Now in this case, we could solve for y equals and then do an explicit derivative, one where y is a function of x, and we would simply have two different functions and two different derivatives. However, it is possible to do these without having to solve for y, and it's also possible to take the derivative even if it's impossible to solve for y algebraically. Now, when we take the derivative, most of the time we have y is some function of x. And whether we think about it or not, we are actually doing implicit differentiation. When we look at this and we ask for the derivative, we don't write the derivative of y as 1. We say that y prime is equal to f prime of x, or dy dx. We never say that the derivative of y is just equal to 1, the way that the derivative of x is equal to 1. That's because when we're taking the derivative with respect to x, they simply don't match. In reality, I could write this, y equals x cubed, say that I'm going to take the derivative of each side in terms of x. So what I'm trying to take the derivative of is y, which we see as dy dx, not 1. And now we're taking the derivative of an x cubed. Now it just so happens that really this is a function, x, that's being cubed. We could think of that as the chain rule and bring the 3 down. The x would now be to the second power. And then the derivative of the inside is the derivative of x with respect to x. That's really why this becomes a giant 1 and we don't have to write it down. So if the variables agree, then we take the derivative, and it just so happens that the dx cancels. It did not cancel when we were trying to take the derivative of y. dy dx is not 1. dx is equal to 1. So for this one, the variables disagree. That means that when I take the derivative using the power rule, I'm not going to have a dx. What I have to think about here is that y is really a function of x. So if I have a y cubed, I really have the function of x being cubed. I just haven't solved for the function of x. I don't know what it is. So when I take the derivative, the power comes down. We reduce by 1. And then the chain rule says we have to take the derivative of the inside. And we know that our notation for f prime could also be written as dy dx. So it's when they don't match that you need to keep that derivative notation at the end. So if the variables agree, the derivative of x would come out as dx over dx is just 1. When the variables don't agree, we take the derivative, but it's 3 dy dx. Here we're doing the product rule, so we have x times y squared. The derivative of x in terms of x is just 1. The derivative of y squared in terms of x, the 2 comes down, y reduces to the first power, but then we have the chain rule involved, and dy dx is not equal to 1. So we're doing that derivative of the inside whether we realize it or not. So then our product rule says we multiply the x times the opposite derivative, and we multiply the y squared times his opposite derivative, which happens to be 1. So this simplifies out as y squared plus 2xy dy dx. So the big rule is, do the terms match what we're taking the derivative with respect to? So the ones that are different, we take the derivative the way we normally would. Y squared becomes 2y, but this is a non-match, so we get a dy dx. 2y, we take the derivative and get 2. The derivative of y stays. 3x, since the x matches, we don't have to tack on anything at the end. And even if we did, dx would just be 1. X squared takes the derivative, gets 2x. If we were to tack something on, dx, for example, it would be unnecessary. Now solving for dy dx means we're going to collect those terms together on the left, move the other terms that don't have dy dx over, factor out the dy dx, and then we can divide the left and the right side by the 2y minus 2 to get our solved answer. So the key is, do the variables match? If they do, you don't have to tack anything on. If they don't, you do have to tack on that chain rule. Okay, so remember the important rules. Differentiate both sides of the equation with respect to x. So that's really important, what you're taking the derivative with respect to. Collect all the terms of dy on one side or the other. It does not matter which side, although I'll talk to you about some tricks and tips for how to make sure you're going to get the answer quickly to be the multiple choice match. Factor the dy dx out, and then finish solving for dy dx. Okay, so we're going to do some practice together. Finding dy dx, make sure, I tend to highlight mine a little bit, that I'm doing the entire equation all the way across. So I don't want to get to part of it and forget to do the very end. I'm taking the derivative with respect to x, which means anything with a y term is special. So taking the derivative of y cubed, I get 3y squared. That's a non-matching term, so it gets the dy dx. I take the derivative of 7y to get 7, and that's a non-matching term, so I write the dy dx. I take the derivative of x cubed to get 3x squared. That's a matching term, so I don't write dx dx, which would really equal 1. I'm then going to factor out the dy dx on the left-hand side since my terms are already collected. I don't have to move anything before factoring in this particular problem. And now, since this is multiplication, the opposite would be to divide over. So my dy dx equals 3x squared divided by the quantity 3y squared plus 7. Number 2 is going to be a little bit trickier because we have to watch out for those products. Now, a lot of students forget about the product because we're very accustomed to a product having parentheses or a product being two very distinct functions multiplied together. We tend to forget that in this case, y is not a variable, it's a function. So when we're doing this one, our 4x squared would have a derivative of just 8x, but our y term would have a derivative of dy dx. So on the first part, I have 4x squared times the derivative of the second part of that product plus the y, which is the second term, times the derivative of the first part of the product. For the second term of the entire original, I have a negative 3y. That's a non-matching term. So I get negative 3 is what I would normally think my derivative would be. But then because it's a non-matching term, I add the dy dx. The x cubed is a 3x squared. Because I'm taking the derivative with respect to x, that's my normal term, I don't have to do anything. And the derivative of a constant is always 0. Now this time I have a little bit of mixed up terms. I have some dy dx terms and some that don't have dy dx. Now, in my decision for how to move them, I would try to move them so I would have the least number of negative signs. The reason I would do that is because the AP exam multiple choice answer will be the one with the least number of negative signs. So if I choose to leave the two dy dx's, I'd have a positive 3x squared and negative 8xy when I move it. So a negative on the right and this negative 3 that's already on the left. If instead I were to try to move both of the dy terms and then also have to move the 3x squared, I would still end up with one positive and one negative on each side. For that reason, I'm going to do the one that's the least amount of work. The least amount of work is to keep the dy dx terms on the left. So I'm going to factor out the dy dx on the left-hand side, and dy dx belongs with 4x squared and minus 3. That means I'm going to move the 8xy over to the other side. When I do that, I end up with a positive 3x squared on that side and minus 8xy. Now the left-hand term is multiplied. To undo that, I'm going to divide by that entire term. So my dy dx is going to equal the right-hand side divided by the product term from the left-hand side. For number 3, again, I want to make sure I'm going all the way across to do the entire derivative. And all of my terms are plain x terms except for the 5y cubed. So that's the only term that has something special. So when I take the derivative of x squared, I get 2x because we're taking the derivative in terms of x. For the 5y cubed, I take the derivative normally, which would be 15y squared. But since I'm taking the derivative in terms of x, that one's a special term. And I added my chain rule. On the right-hand side, x plus 9 is just 1 because the derivative of 9 is 0, and we're doing the derivative in terms of x, so we don't have to tack anything on. So now the 15y squared dy dx equals 1 minus 2x. So my dy dx term is the right-hand side divided by the left-hand side product term. Now for number 4, notice that we are not doing the derivative in terms of x. We are taking this derivative in terms of t. That means anything that has a non-t term in it is going to be special. Also, watch out for the second term being a product. The derivative of t cubed with respect to t is 3t squared. Plus, I have a product. My product is the first term times the derivative of the second term. The derivative of y is normally 1, but we have to add on the dy dt because, again, doesn't match. Plus, in my product, and again, don't forget to do the product rule because we're so worried right now about doing our dy dx's and dy dt's, we sometimes forget all of our other rules. So we had first times the derivative of the second, plus the second term, which was y, times the derivative of the first term, which is 2t. So that was all just doing my product rule. Now we need to take the derivative of negative 10y to the fourth. We get negative 40y cubed. And because this is a y term, not a t term, we have to put the dy dt on there. Equals, the derivative of 0 is 0. So now this time, I have a positive dy term and a negative dy term, and two positive terms that don't have dy. If I move both of these two terms to the right-hand side, I will have three negatives altogether, the original negative here and the two after I move. Instead, I'm going to keep the 3t squared and the plus 2ty on the left-hand side. I'm going to instead move the two dy terms over, because that gives me one positive and one negative there. That's the least amount of negatives I can make in the problem. Now, from there, I'm going to factor out on the right-hand side the dy dt term. That leaves me with 40y cubed minus t squared as my product term. So the left-hand side this time, divided by the product term from the right-hand side, is equal to my dy dt. Now, notice that number 5 is asking for dy dx, but at a point. You're going to like these a little better, because it saves us some time algebraically that becomes just arithmetic. Now, we have a product here. We're taking the derivative in terms of x. So, keep the first term, take the derivative of the second term. Keep the second term, take the derivative of the first term. That's how a product works. So 2x squared goes with the derivative of the second term, which in this case is 1 dy dx. The derivative of a single variable appears to be 1, but this is the non-matching term. And then we keep the y term, and the derivative would be 4x, and we don't add anything on because it is the matching term. So notice you're not adding a dy dx to every single y you see in the entire problem. You're only putting a dy dx when you're actually taking the derivative of that y. Now, taking the derivative of negative 4y cubed, we get negative 12 y squared. That is taking a derivative of the y term. So we're going to add that on for the chain rule, equals the derivative of 4, which is 0. Now again, I have to think about my negative signs. If I keep the two dy terms and move over the non-dy, I'll have a negative on the left and a negative on the right. If I keep the plain term on the left-hand side and move the other two terms over, I'll still only have one negative and one positive, so that's going to be my least number of negatives. So I'm going to keep 4xy on the left-hand side. To the right-hand side, I'm going to move over. So when I move them over, remember they switch signs algebraically. So 12y squared dy dx minus 2x squared dy dx. Now, from here, I can, this is where the algebra part comes in a little bit better, I can avoid having to do as much algebra with all of the letters. Since I don't want the derivative at all values of x, where up above we were looking for the function of dy dx, we're not looking for a function here, we're looking for a constant at a specific value. Make sure you plug them in carefully, don't mix up your x and y. So you have 4 times the x value of 2 times the y value of 1 equals 12 times the y value of 1 squared dy dx minus 2 times the x value squared dy dx. So I have 8 equals 12 dy dx minus 8 dy dx. So 8 equals 4 dy dx. So dividing both sides by 4, I get 2 equals dy dx. So this is only the value of the slope at the point 2, 1. So we could use point slope form if we wanted to write the tangent line. Okay. For number 6, again, we're back to being asked for the entire function. So I don't get to kind of slip through and do just arithmetic now. I'm going to have to actually solve for dy dx in this case. I do need to be cautious to make sure I'm doing the entire equation all the way across. Sometimes we start doing a quotient rule or something difficult and we forget to finish the problem. So my low part is y plus x squared. The derivative of the low part is dy dx plus 2x. The high part is x minus y cubed. So the derivative of the high part is 1 minus 3y squared dy dx. So the left-hand side, which is a quotient rule, has a derivative of low d high minus high d low over the square of what was below. Whew, that seems like a lot, but we're not even quite done. We still have to do the derivative of the right-hand side of this entire equation, which is just 1, thankfully. Now I'm going to cross multiply. I end up with y plus x squared times the quantity 1 minus 3y squared dy dx minus x minus y cubed times the quantity dy dx plus 2x equals, when I cross multiply, that denominator comes over to the right hand side. Now, in order to get the dy dx on this one isolated, I'm going to have to FOIL these out. When I do that, I get y minus 3y cubed dy dx plus x squared minus 3x squared y squared dy dx minus x times dy dx minus 2x squared plus y cubed dy dx plus 2x y cubed equals y plus x squared quantity squared. Cool. So now, gathering together my dy terms, don't forget to take the sign with it. There's 1, 2, 3 negatives on the left. If I move the other terms over, I'm going to end up with 2 more negatives on the right. If I move the other terms instead, I'll be a little bit better off. So I'm going to have the x squared and the negative x squared, negative 2x squared rather, and then I have a positive 2xy cubed. So 2xy cubed minus x squared are the only non-dy terms besides the minus y plus x squared quantity squared when we move that over, equals. Now when I move all the dy terms over, I'm going to go ahead and factor that out. This becomes a positive 3y cubed, a positive 3x squared y squared, a positive x, and then another positive 3y cubed when it moves over becomes negative. So I really could have done that as a 2 right here. So we'll fix that. So now the left-hand side divided by the product from the right-hand side equals the dy dx. That's really one of your worst cases for algebra. Oops. Similarly, here we have a combination of products. There are some ways that we could make this a little bit easier. Notice I'm highlighting to make sure I do everything. I don't want to have this 4y run together. I could rewrite this as y equals, factor out an x squared, factor out a y squared, and then have y plus x. Then really we have a triple product. I see a lot of people do that and then not get their product correct. So that's going to be a little worse than doing the original two products. So a lot of people want to factor out. That doesn't always work well. Also, this original equation is defined as a y equals, but not a isolated y. It's not a y equals in that there's y, only one y on the left. So we can't really isolate the y variable here. So we're not really going to be able to get rid of the products, and these two products we'll have to deal with. We're taking the derivative with respect to x. That means the derivative of y is 1 dy dx, because that's the non-matching term. Our product rule for the first product is x squared multiplied by the derivative of y cubed, which is 3y squared dy dx, plus the derivative of x squared would be 2x, the y cubed we can keep, and the derivative. So that's just my first product. My second product term, I have x cubed. The derivative of y squared is 2y dy dx, plus y squared times the derivative of x cubed, which is 3x squared. So the other product. Now, I have dy dx on the left-hand side, 3x squared y squared dy dx, plus a 2x cubed y that has a dy dx, plus 2xy cubed, plus 3x squared y squared. Now, if I move all the dy terms to the left, I'll have two negative dy terms. Everything else will be positive. If instead I move the non-dy terms to the left, they would both be negative, but I would also have to move this dy term over, and it would end up negative. So the least amount of negatives I can have is just to collect the dy's on the left. So I have 1 dy dx on the left already, minus 3x squared y squared dy dx, minus 2x cubed y dy dx equals 2x y cubed plus 3x squared y squared. Factoring out the dy dx, there's a reason I wrote that 1 for emphasis there. A lot of students forget that 1 and put it as kind of as a 0. They omit it altogether. But it's 1 minus 3x squared y squared minus 2x cubed y times the dy dx equals my right-hand term. So dy dx is equal to the entire right-hand side divided by the product term from the left-hand side. Now, we're going to find an equation of the normal line, not the tangent line, the normal line, perpendicular to a tangent line at the point 3, 1. So remember, a tangent line just touches. The normal line is going to be perpendicular to that. Okay, so we have quite the chain rule here. The 2 is going to come down. So we have 16 x squared plus y squared to the first power now times the derivative of the inside. If you forget the parentheses here, your entire problem is going to be wrong past one of the points that you could earn. You're only going to be able to earn 1 point if you forget those parentheses. Okay, so now the 2 came down, we made 16. X squared plus y squared is now to the first power. The derivative of the inside must be in parentheses. 2x plus 2y dy dx. So that's the first part that we've done the derivative, was just this part. We didn't take a derivative over here of the x squared plus y squared. That was our guts. So we brought it down, kept the guts. No dy dx here. Times the derivative of the inside equals, now this one you could kind of think of as 100x squared minus 100y squared. Might make it a little easier. I get 200x minus 200y dy dx for that second part, because only this part really has the derivative that's implicit. You're going to like this part though. We're doing this at the point 3, 1. That means x equals 3 and y equals 1. If x is 3, this is 9. Y is 1, stays 1. X is 3, we get 6 plus 2 dy dx equals 600 minus 200 dy dx. Now, please watch your PEMDAS. You must do multiplication and division before addition and subtraction. This does not become 8 dy dx. It's a 6 entirely separate from the dy term. It is not 8 dy dx. This is also not 400 dy dx. For it to be 400 dy dx, this would have to be in parentheses, and it is not. So 16 times 10 is 160 times the 6 plus the 2 dy dx. So I'm going to go ahead and write this out on the left side again. 600 minus 200 dy dx. When I distribute, 6 times 16 is 96, so 960 plus 320 dy dx equals 600 minus 200 dy dx. So my dy dx terms collect over. My 960 is also going to go to the other side. So I'm going to have 520 dy dx equals negative 360. Dividing each side by 10 is pretty easy. Then our dy dx equals negative 36 divided by 52. 52 is 4 times 13. 36, negative 36 is negative 4 times 9. So the 4's cancel, and my slope of the tangent line is negative 9 over 13. That is not the slope of the normal line. The normal slope is perpendicular to the tangent. So the slope of the normal line is the opposite reciprocal. Opposite reciprocal is a positive 13 over 9. We already have the point. We now have the normal slope. So we can write this in point slope form. Y minus 1 equals 13 over 9, parentheses, x minus 3, close parentheses. Remember, on a free response, we are never going to simplify that out. Okay, circling to make sure I do the whole thing. The derivative of x is 1. The derivative of y I'm going to write as y prime. The derivative of 3y squared is 6y times y prime. So I can really think of the derivative of y as being 1 times the y prime. 6y times the y prime. 4y cubed becomes 12y squared times the y prime, because we need that when we're taking the derivative as y prime. Y prime is understood to be in terms of x. So now I can factor out the y prime. That leaves me with 1 plus 6y plus 12y squared as my product term. So the left side divided by the right side is equal to my y prime. Correct answer is A. So I'm going to circle, make sure I do the whole thing. I'm also going to make a note of the fact that I have a product. 2x has a derivative of 2 when we're taking the derivative in terms of x. The product is first term times the second term's derivative, second term times the first term's derivative. So just this part is my product. So x times the derivative of y, which is 1 dy dx. I'll write it as y prime just to save space. Y times the derivative of the x term, which is 1, because we're taking the derivative in terms of x. Now I can move on and do the derivative of y squared, which is plus 2y times y prime. So I'm going to subtract the y to get it over with the 2. So I get 2 minus y equals x times y prime plus 2y times y prime. Factoring out the y primes, I get x plus 2y as my product term. So the left-hand side divided by the product term, x plus 2y, is equal to my y prime. So I'm looking for x plus 2y to be on the bottom, a positive 2 and a negative y. So C. For number 11, I'm going to circle. I'm going to make sure I do the whole thing. And I'm going to make a note of my products so I can make sure that I do them. We're taking the derivative in terms of x because y prime is understood to be dy dx. Derivative of x squared is 2x. Derivative of y squared is similarly 2y, but it has the dy dx on there. Now my product, I'm going to keep the 2 and do my product here. So I have x times the derivative of y plus y times the derivative of x. So now I have 2x plus 2y times y prime equals 2x times y prime plus 2y, because that 2 distributes across the product. Now, whether I move to the left or to the right doesn't really matter. I'm going to end up with a negative on each side regardless. So I'm going to look at my choices. I have y minus x minus y, really not a clear indication yet. What I do notice is I can factor out of 2 from everything. So I have a 2 x plus y prime equals a 2 x y prime plus y. I never cancel unless I can factor, but in this case I can. That kind of tells me I probably don't have this 2 left here either. So now I have my y prime terms. If I collect them together, I can pull them to the left. I have a y times y prime minus an x times y prime. If I move this one over. If I move the other x term back to the other side, I'm going to have a negative x and a positive y. Factoring out my y prime, my product term is now y minus x, and the right-hand side is negative x plus y. So if I divide the right-hand side by the left-hand product term, negative x plus y, divided by y minus x. Those are not identical terms, apparently, or they don't appear to be right away, except now, if I were to rewrite this as negative x plus y, and notice that bottom term is also a negative x plus y, this in fact does cancel, and the answer is just 1. What that tells me is that this shape, it's technically 2 functions, actually simplifies out to be a y equals x plus a constant possibly, because it just has a derivative of 1. In fact, if we were to subtract the 2xy, notice that this is really x minus y squared if I factor it. So it's pretty nice that y equals x. You're not really required to know that necessarily, that it would simplify out to that. Just be able to do the implicit differentiation. It's kind of interesting though. Okay, I'm going to circle. Make sure I'm doing the whole thing all the way across. I'm going to label my products. Product here, product here. So I have x squared times the derivative of y cubed plus y cubed times the derivative of x squared. So that was my first product. Then I have 5x times the derivative of the y, which is y prime, plus the y term times the derivative of 5x, which is 5. So I've done both of my products. Then I have the derivative of x, which is 1, minus 4y prime equals 0. So my y prime terms are 3x squared y squared times y prime. I'm going to factor it out. Plus a 5x and minus a 4. So I've basically collected together all of my y prime terms. So 3x squared y squared, 5x, and negative 4 are all multiplied by y prime. So that's going to equal the non-y prime terms. So I'm going to move them over across the 0. So then I'm going to have a negative 2x y cubed a negative 5y, and a negative 1. So I have my y prime is equal to the entire right side divided by the product from the left side. So the correct answer is B. Okay, the next one says, what is the slope of the tangent line at the point 1, 3? So slope of the tangent is just y prime. It's not the normal, so it's not perpendicular. And we have the point. That's going to make us happy because we get to substitute in nicely. I'm going to circle to make sure I do the whole thing. And I have two different products. So we have x squared times the derivative of the y term plus y times the derivative of the x squared term. For the next product, I have x times the derivative of y squared, which is implicit, plus the y squared times the derivative of the x term. That's my second product. Equals the derivative of 12 is 0. This is the happy part. X is 1, y is 3. X is 1, we have 1, y prime. X is 1, so this part's 2. Y is 3, so 3 times 2 times 1 is just plain old 6. And then we have x times 2 times y. So 1 times 2 times 3 is 6 again, but that's a y prime term. We can't combine the non-y primes with the y primes. You've got to be very careful. And then y squared is 3 squared, so 9. And then we're still equal to 0. So that means if I collect on the left-hand side, I have 7 y primes. I move the 6 and the 9 across the equals, puts a negative 15 on the right-hand side. So y prime is equal to negative 15. Oh, my pen's going a little crazy. Give me a second. I can fix it. So my y prime is negative 15 divided by 7. A. Okay, so this time we're going to find the equations of the tangent lines, so there's more than one, to the curve at x equals 0. So we need the tangent slope, so we're going to do the chain rule 2, x minus y to the first power, times the derivative of the inside must be in parentheses because there's multiple terms. So 1 minus y prime equals, the right-hand side derivative is 1 plus 1y prime plus 0, because the derivative of 2 is 0. And we're going to use this at x equals 0. Problem is, at x equals 0 doesn't really give us a full solution. Right now, if we put x equals 0 in, we get 2 times negative y, 1 minus y prime, equals 1 plus y prime. So negative 2y distributes to the 1 and to the negative y prime. So plus 2y, y prime, equals 1 plus y prime. So 2y, y prime, minus 1y prime, equals 1 plus 2y. So y prime times 2y minus 1 equals 1 plus 2y, and y prime equals the right hand 1 plus 2y, all divided by quantity 2y minus 1. That really didn't give us a constant slope. We need a constant slope to have an equation of a line. So there's a little something missing. For me to finish, I need to know what y is. Y is not found from the derivative. Y is a point on the curve. On the curve means I need to go back to the original. If x is 0, I get negative y squared which is positive y squared because the negative's in the parentheses. So negative y times a negative y is positive y squared, equals 0 plus y plus 2. So y squared minus y minus 2 equals 0. That's factorable as y minus 1, y minus 2, y plus 1 equals 0. So that means that y equals both 2 and negative 1, which is not surprising given how complex this curve equation is. That means there's two equations for two different lines. We have the point where x is 0, y is 2, and we have the point where x is 0 and y is negative 1. We need to find the tangent slope that corresponds to each of those. So if x is 0, we already have the derivative, but we need to substitute in the y being 2. So the slope of the tangent is 1 plus 4, because 2 times 2. Then 2 times 2 is 4, minus 1 is 3. So 5/3. Similarly, for the tangent line of the other line, using y equals negative 1, 1 minus 2 is negative 1 in the numerator. Negative 2 minus 1 is negative 3 in the denominator, and our slope is positive 1/3. So the first tangent line equation is y minus 2 equals 5/3 times the quantity x minus 0. You don't have to write the minus 0. The second linear equation is y plus 1 equals the slope of positive 1/3, and again x minus 0. So if you need the x and the y point for your derivative, and you're only given the x point, you will always go back into the curve, the original curve, to find the x or y value for your coordinate point. For number 15, we gave you the entire point, negative 1, 1. Equation of the line tangent. Notice it only says line. There may only be one. So we're going to circle. We have a chain rule here, but no product. We have a product rule for this part. So our chain comes out as 3 times the sum of x squared plus y squared, now raised to the second power. And here's our chain times the derivative of the inside is 2x plus 2y dy dx equals, our product has 8x squared times y squared. So I keep the 8x squared. The derivative of y squared is 2y dy dx plus the y squared I'm going to keep, and this time I'm going to do the derivative of 8x squared to get 16x. Now this one's nicer because we have the x and the y. We just have to be careful substituting in. So negative 1 squared is 1, positive 1 squared is 1, and that whole quantity is still being squared. Negative 2, positive 2 dy dx. Remember not to try to combine the non-dy terms with the dy terms. This does not become 0. We now have 16. Negative x squared becomes positive 1. Y is already positive 1. And then we have the dy dx. X is negative 1, so this becomes negative 16. And then y is squared, but that's still just 1. Again, we cannot combine these terms. They're not matching terms. Over here on the left-hand side, 1 plus 1 becomes 2. 2 squared is 4. 4 times 3 is 12. So we're really distributing 12 across this sum. So we have negative 24 plus 24 dy dx equals 16 dy dx minus 16. I'm going to add the 24 over. 24 minus 16 is 8. 24 minus 16 goes the other way as well, is also 8. So we have 8 dy dx equals 8. So our derivative is just 1. It is not a constant 1 all the time. It just so happens at this point the slope is 1. Not everywhere. We would definitely have had a much more complex slope. So now we can write the equation of the line using point slope form. Y minus 1 equals our m, which is 1, x minus negative 1. You can leave it that way, even though I know it's very, 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 very tempting, because y would equal x plus 2, which is fine as well. But in standard form, we would have negative 2 equals x minus y. So we can do this in slope-intercept. We can do this in standard form, but we're going to leave them in point-slope form unless it's a multiple choice. If you're getting specific points for being able to find the slope and write the line, you're not getting any extra credit for simplifying on that. Okay, so for this one, we want to make sure that we understand what it's asking. It's asking us to find all points on the curve. So we need to find coordinate points on the curve where the line's tangent have a slope of negative 1. So let's think about what that means. To have a slope of negative 1 means that we have a downward slope of negative 1. There are going to be two places on this curve where that occurs. It can occur in the first quadrant, because those are negative slopes, and in the third quadrant, because we have negative slopes there. And specifically, we want the slope to be negative 1. So we can't have any points in the the second or fourth quadrants. So we are looking for 2 points. The slope of negative 1 does not mean we're substituting negative 1 in. It means our derivative has to equal negative 1. So, using the power rule, the derivative of x to the 2/3 is 2/3 x to the negative 1/3. The derivative of y to the 2/3 is 2/3 y to the negative 1/3 times dy dx. The derivative of 8 is 0. So if I move over, I have 2/3 y to the negative 1/3 y prime equals negative 2/3 x to the negative 1/3. Dividing both sides by 2/3, that'll cancel. And then dividing both sides by the y term, not the dy term, I have x to the negative 1/3 divided by y to the negative 1/3, which actually comes out to be, both of them with a negative power means they're kind of in the wrong spot, y to the 1/3 divided by x to the 1/3, because that's what the negative power does. Flips it over. Now we want to have a slope of negative 1, which means we're going to substitute in negative 1 for y prime. That now means I can cross multiply, and negative x to the 1/3 equals positive y to the 1/3. I can cube both sides. Cubing both sides to get rid of the 1/3 power. This is an odd power, so I still have a negative, because 3 negatives is still a negative, but then I have negative x equal to positive y. That should make sense, since if we look at where this would fall, y equals negative x, and y equals x fall in here. Okay, now remember what I had said before about finding points on the curve. If we're looking for points on the graph, then we want this to be able to substitute in for here. That means that x to the 2/3 plus y to the 2/3 has to equal 8, and we can substitute negative x in for y. That means that x to the 2/3 plus x to the 2/3 equals 8. That's because of this square. When we're squaring a negative, that's the cube root. The cube root can have a negative, but when we square it becomes positive. Remember, you have tree, and roots of your tree down on the bottom. Kind of looks like grass, but it's not. It's a power line. Those are my roots. I guess I could have drawn them more like that. Okay, so that means that I have 2x to the 2/3 equals 8. So x to the 2/3 equals 4. So x equals 4. Instead of the 2/3 power, algebraically it becomes the 3/2 power. But I end up needing a plus and minus. So when we write it as the power, people tend to forget that they need the plus and minus. So we'll look at why we need the plus and minus. This is really the cube root of x squared equals 4, which is why up here the cube root squared became positive. So if I get rid of the cube, x squared equals 4 cubed, which is 64. So x equals plus and minus the square root of 64, which is plus and minus 8. Be very, very careful that you do not try to write this as plus and minus 8 equals and plus and minus 8 for the y value. That would be absolutely wrong. These 4 points are not all solutions. X equals plus and minus 8. If x equals 8, y equals the opposite of x, negative 8. If x equals negative 8, y is equal to the opposite of x, positive 8. We do not get all 4 points. If x is positive 8, we do not get positive 8 as an answer for y. We only get the point 8, negative 8, and the point negative 8, 8. Excuse me. Okay, so we're going to find all points on the graph where the derivative is 0. Now I can kind of draw a circle to show where I think that should be. There's going to be 4 of them this time. Not because of the circle, it just helped me find them. Where I have 0 slope. So we have the chain rule, but no product rules. So the chain rule, we have 2x squared plus y squared to the first power times the derivative of the inside. So derivative of the outside, derivative of the inside, equals, on the right-hand side, 4x minus 4y dy dx. Notice it says we want y prime to equal 0. This actually makes me very, very happy. Now the smiley faces aren't working as well as I would like them to, so there we go. That means that I can take y prime equal to 0 and put that in everywhere there's a y prime. So I'm going to have 2x squared plus 2y squared times 2x And since y prime is 0, this whole part becomes 0. Equals 4x. And because y prime is 0, this whole part becomes 0. So now I have 2x squared plus 2y squared times 2x equals 4x. If I move this over, 2x squared plus 2y squared times 2x minus 4x has to equal 0. So I can factor out a 2x. 2x squared plus 2y squared minus 2 has to equal 0. 2x equal to 0, or 2x squared plus 2y squared minus 2 has to equal 0. X equal to 0, or 2x squared plus 2y squared equals 2. I divide every single term by 2, I get x squared plus y squared has to equal 1. Now, if x squared plus y squared equals 1, or x equals 0, we need to find all points on this curve. So, let's try x equals 0. If x equals 0, then we get y squared equals negative 2y squared. So we're putting x equals 0 here, we get y squared squared. X equals 0 here, we get negative 2y squared. So y to the 4th equals negative 2y squared. That's not possible, because y to the 4th is always positive, y squared is always positive, so negative 2y squared, but you can't have an always positive equal to an always negative. You could also see that you would have y to the 4th plus 2y squared would have to equal 0, and a positive plus a positive just can't equal 0. So x equal to 0 is not an option. So now we're going to go with x squared plus y squared equals 1. That looks pretty bad, but it's not going to be as bad as you think, because look right here in our equation, x squared plus y squared. That's nice. X squared plus y squared equals 1 means 1 squared. So x squared plus y squared, the whole thing got replaced with 1. This right-hand side, however, is not x squared plus y squared, so we're going to have to do a little bit more work. So x squared is equal to 1 minus y squared is something we can substitute in. So we have the left-hand side was just x squared plus y squared equals 1. The right-hand side is 2x squared, which we're going to replace with 1 minus y squared from here, minus 2y squared. So 1 equals 2 minus 2y squared minus another 2y squared. So now we have negative 1 when we subtract the 2 over equals negative 2y squared, negative 4y squared. We can combine these like terms. So now when we divide by negative 4, we have positive 1/4 equals y squared. Well, a positive equal to y squared is possible, so that would mean that y squared equals plus and minus the square root of 1/4, which is plus and minus 1/2. That makes sense because we noticed our tick marks here are at 1. It would make sense that we're going to get a half approximately here. So now we have to go back and figure out what x would be. So since x squared plus y squared equals 1, we know that y squared equals 1/4. X squared plus y squared, which was 1/4, has to equal 1. So x squared equals 3/4. So x is going to equal plus and minus the square root of 3/4, which is plus and minus the square root of 3 over 2. Now in this case, both y values would have given me a positive 1/4, and both y values correspond to both x values. So in this case, we could write plus and minus root 3 over 2. Both go with plus and minus 1/2, because the positive root 3 over 2 does go with both, and the negative root 3 over 2 for x does correspond to both values. So we do get 4 matching points for that one. Okay, for this last problem, oh, I have little flashes here. We have a tilted ellipse. Among all the points on this graph, find the largest and smallest values of y, and then the largest and smallest values of x. So let's think about where that would be. Our highest value for y is going to be where y prime equals 0. And our lowest value for y is going to have the same situation. Our highest value for x is over on this side, is actually going to be where y prime is undefined, our vertical tangent line. And our smallest x value is also going to be where y prime is undefined. So using our derivative, we have a product, and we have to make sure we take the whole derivative. So our derivative is 2x, and then we have a minus x times the derivative of y, and then we have a y times the derivative of negative x. That was our product, negative x times y. And then we have plus the derivative of y squared, which is 2y y prime, equals the derivative of 3, which is 0. So this time, we're going to have to do this a little differently because we're looking for 0 slopes and undefined slopes. So that really means that we need our y prime fraction. So we have negative x times y prime plus 2y times y prime equals, and I'm going to move these terms over that are not y prime terms. So it makes it a positive y and a negative 2x. So factoring out my y prime, I have a positive 2y and a negative x, and that's equal to y minus 2x. So dividing by the product term, we have the derivative is y minus 2x over 2y minus x. So for our slope to equal 0, that really means only the numerator can equal 0. So for 0 slopes, I want y minus 2x to equal 0, or y to equal 2x. I'm going to use that by going back into the curve because I want points on the graph. So that means we have x squared minus x times y, which was 2x, plus y squared, which means the 2x quantity squared, equals 3. So x squared minus 2x squared plus 4x squared equals 3. So 3x squared equals 3. X squared equals 1. So x is equal to plus and minus 1 when we have a 0 slope. I still need points on the curve. Sorry, my screen's jumping around a little bit. But we don't have to go all the way back to the original curve. We already have a requirement for these points. We already knew that y had to be 2x for the horizontal slopes. So if x equals positive 1, y equals 2. If x equals negative 1, y equals negative 2. We cannot do the plus and minus for these because it's not all 4 points. We only have 2 points where the slope is 0. So at those points, 1, 2, and negative 1, negative 2, that's where we have the max and min y. So the max and min y are y equal to plus and minus 2, but not the points as plus and minus. Now, to find these undefined slopes so we can figure out where x is the largest, undefined slope, for the slope to be undefined, it means only the denominator equals 0. So 2y minus x equals 0. So 2y equals x. I'm going to put that back into the original curve. The original curve was x squared. So x is going to be replaced with 2y, x squared, minus x, again replaced with 2y, times y. So x squared minus xy plus y squared equals 3. So squaring, we have 4y squared minus 2y squared plus y squared equals 3. So 3y squared equals 3 gives me y squared equal to 1. So y equals plus and minus 1. We go back to our requirement for undefined, meaning x equals 2y. So if y equals 1, x equals 2. If y equals a negative 1, since x is double the y, we get negative 2. So that means that my max and then x values are x equal to plus and minus 2. It's really important that you learn how to do vertical and horizontal tangent lines and where those occur.